All right, so last time we started chapter 6, right? I believe. Got through chapter 6.1, I believe. And already had a few questions from chapter 6 homework, which is good because that means you're working on it. I have not answered all those questions yet, and if we have time at the end of the day today, we will answer some homework questions. But I would like to get through as much as we can so that if we need to, we can have all day Friday to answer questions as well, since we missed last Friday. Before we get too far into things, though, I do want to, well, I forgot to actually set up the lab if I'm remembering things here. Let's take a look here. Yeah. To okay. Search assessments. Wait, what just happened? That's not what I wanted to do. Okay, then to all right. Excellent. So chapter 6, Newton's laws. So in chapter 5, we did not do a experiment. But in chapter 4, we did. And the one we did was lab 4. That's good. Okay. Now we want to do we want to look for this is we're looking for a drive. Google Drive repository. That's what we want. And we want to look at our. Nope, that's not what we want. Yeah, that's what we want. Right there. And we're looking for lab 5. Let's see what we've got here. This is the one. Okay. So we're going to use lab 5 activity for this. We're going to see, I think we want to download that. There we go. And then we're going to put it into your lab here so that you can see it. And then lab 5 will be ready, which is actually happening during chapter 6. We should have done it during chapter 5, but we didn't. So this will be, oh, this is actually under, so actually be under experiment 6, which is fine. Download. Yeah. Let's see, we're not gonna use a URL. We're going to insert a file. That's what we're gonna do. Downloads, Lab5 activity, open, load. Okay, so there it is. So now you've got that under lab 6, which is due. It's calling it experiment 5. Is that right? I don't. Where is experiment 5? I don't even see that in my thing here. Experiment 5 is not there. Where did experiment? Oh, the experiment 5 is all the way down here. That's not where I want it. I will move it. It's in the calendar for this week. So I will move that back to where it needs to go eventually. We do have experiment 5 this week, just so you know. It's in the calendar. It's just not in the, it's not in the, I can actually move it right now. Let me figure out where I put it here. Put it in chapter 6.
I think you might be in general physics.
Am I in general physics?
I think that's what I just saw.
Oh, no,
Is
that's,
that us?
no,
That's
this
us?
is where I'm supposed to
Okay.
be. That's where I'm supposed to be.
Okay.
So I made that mistake before, so it was a very good thought that I would make it again, but I'm actually in the right place for once. All right, so let's move this to chapter 6, and we'll move it after the homework or something. I don't know where, it doesn't really matter. I'll fix these. I can fix the names of these later, but we will be doing experiment 5 this week with chapter 6 homework, even though those don't match up in numbers, just because that's the way I ended up doing it. Eventually I'll fix that, put experiment 5 with chapter 5, and then we'll have a different one for chapter 6. And then hopefully next week we'll get everything all fixed up as far as that goes, because we will have a, when we get into work in kinetic energy, we'll have another experiment to do there. Potential energy, conservation energy. We'll probably have an experiment to do for chapter 8 and not for chapter 7, and then we'll have one for chapter 9 for sure. And then we'll be on to our next exam and almost done with the class. All right, so let's go back to where we are here in whatever chapter we're in, chapter 6. There we go. Newton, so this chapter again is just different ways of using Newton's laws and different forces that are involved. This first section, we did a bunch of examples of different forces in different situations that were kind of familiar to what we'd been doing so far. Sums of forces, and in the case of the last 2 examples, we had some calculus involved, because they gave us the velocity as a function. They gave us the velocity as a function of time, or no, they gave us the acceleration as a function of time, and we had to come up with a formula for the velocity. So the acceleration, of course, is the derivative of the velocity. So the velocity is the integral of the acceleration, right? So they did that, they worked through that. I don't know that I gave you any problems involving that. I don't think I did, but I could be wrong. I think that I put 25 homework problems in the homework, which may seem like a lot, but there's a lot of them that are actually fairly quick, fairly simple. Most of this chapter is just about kind of ingraining the idea of Newton's second law into our psyche so that we always know to go to it when it's necessary, when it's appropriate to use the Newton's second law. We also talked about, tension in ropes and cables, something that we gave some time to. We also talked about these situations where you have multiple objects connected and by something that has tension in it, and how you can treat them as a single system, or how you can treat them separately with things like the tension that connect the two. And so that's something to think about. Sometimes they will ask you what's the net force on the system, on the entire system, which means both blocks and the cord are acting as a system. But sometimes they'll ask you what specifically is a force on one of the blocks or the other block, maybe the friction on one block. And so then you have to kind of treat it separately. These are these can be fairly complex problems to kind of figure out how to set them up. Usually the math in the end is not any more difficult than usual, but setting them up properly is certainly the challenge in these problems. And we will hopefully get some time to do some more examples of that to help you to see how that's done. I've done many examples of these on videos for chapter 6 in the past. So if you're struggling and you're stuck and you can't get a hold of me, you can always look through past videos of chapter 6 that I've done. And there are also many videos of these kinds of problems on YouTube as well, just so you know. Also, as we get into this portion of the class, many students start to feel like they need extra time and need extra help on homework, and I'm totally fine with that. I just want you to be aware of I want to remind you of all the resources that you do have. I do not believe that we have, well, that's not true. I do have, I think, 1, maybe 2 students on McCook's campus that have taken this class before. If they were willing to be tutors, we could set that up, I think, possibly. But I don't think there's anybody on this campus who is taking this class who is still here at the college. I'm thinking, and I don't really think I know anybody. But anyway, that's okay because I'm here on this campus and I'm more than willing to help out. I've been meeting regularly with a student from my other physics class in the afternoons, so I am often here in the afternoons. And if you want to just ask me to be here in the afternoon after class to come in and work on homework, just tell me and I will make it happen. I'm also available between classes. We also have, of course, the videos that are available and different things, different tools through MyOpenMath, but we also have online tutoring through BrainQuest, BrainFuse, which is you can find on your Canvas. Get onto Canvas in any class that you're taking and you can click on BrainFuse and use it. I've had many physics students who have used it with great success. So they're available 24/7, and that's another useful thing. And also, don't forget to email me or through MyOpenMath when you have questions about the homework. I try to get those as much as possible. If you email me late at night these days, I'm trying to get to bed earlier because I'm trying to fix my sleep cycle. I'm getting too old to stay up late at night. So I'm trying to go to bed a little bit earlier so you're not likely to catch me as much at night as you used to be able to. But that probably means I'll be waking up earlier. I usually wake up at about 5:30 and I'll probably be getting up at 4:30 with going to bed earlier. So I can only sleep about 6 hours a night. So if you email me late at night, I'll very likely catch that earlier in the morning, but I'm still not quite to the point where I'm getting up much earlier. So besides that, if you have any other questions or concerns, or if you need to go back and finish a homework assignment, I don't want you to feel like you can't do that. You can do that. And as long as it's not the entire class worth of assignments, I'm usually pretty open to to opening those up and helping you get caught up. If it's the entire classwork, I may impose some kind of late penalty, but I still want you to get through this class so that you can finish the class, get a good grade that you're happy with and move on in your education. I do not want to hold you up in your education. I want to help you through your education. So make sure that you send me a note if you need help, if you need to make something up, if you need to get caught up. We want to do that as soon as possible. We don't want to be doing it all at the end of the semester. So now that I've mentioned all of that, I think we're good to go. Moving forward here. So let's see here. We're going to move on to section 6.2, which is all about friction. So friction is something that we all talk about in everyday life, but it can be a little more complicated than we imagine. First of all, just a basic definition, friction is this thing that opposes relative motion between systems in contact. Now, to be very clear, it opposes motion whether or not the motion is actually occurring. Friction can oppose motion that is trying to occur. For example, if you're moving from one house to another and you're filling boxes full of books, and the boxes are really heavy, and you can't lift it, so you just try to slide it along the carpet. Everyone knows that when you try to slide a really heavy box along the carpet, you push, and it's maybe not quite enough to get that heavy box moving, so you push harder. And maybe that's not enough, so you push harder, and then finally you get it sliding. And what happens? We've all done this. Is it easier to keep the box moving, or is it easier, well, which is harder, keeping the box moving or getting it to move in the first place? Which one is more difficult?
Getting it to move in the first place.
Right. We've done that before. And so friction is a little more complicated. Getting it to move in the first place requires more force. It's more difficult to do. Keeping it moving is actually a little easier to do. So that suggests there's two kinds of friction, right? That suggests that the friction changes in some way from one kind of friction to another. But it always opposes the motion, right? Did we talk about this before, or am I thinking my other class? I'm thinking of my other class. I am having the hardest time separating my class.
You mentioned a little bit of it with friction,
Oh, did I?
but not a whole bunch.
Okay. Well, anyway, that idea suggests that there are a couple different kinds of friction, but friction is the friction is always going to oppose movement that wants to happen, or something is trying to move something else, and friction will be the thing that opposes that. Because it opposes it, it is always going to point in the opposite direction of the impending motion, or the opposite direction of the actual motion. So if you're trying to push your box to the north, then the friction will be pushing to the south. If you're actually pushing your box to the north, then there will be friction that is essentially like slowing down your motion or opposing your motion. That is going to be to the south, right? It's always going to be in that opposite direction. The two types of friction, we have names for them. We call one of them static, we call the other one kinetic. Static meaning the kind of friction that prevents something from moving is static friction, because things aren't actually moving. And the kinetic friction is the friction between objects that are actually sliding past each other. And that sliding past each other is really important, because in the definition it says relative motion between the surfaces. That means sliding past each other. When you have a wheel rolling on a surface, a wheel rolling on a road, there is actually there's no relative motion between the surface of the wheel and the surface of the road if the wheel is rolling. Why is there no movement? Well, you think about it, as the wheel rolls, and I can't, I'm not sure that I can think of a animation that can do this, but essentially as the wheel rolls, it comes in contact with the ground, And at that moment, as it's in contact with the ground, it's not sliding past the ground. It's rolling across the ground. And if you take a snapshot of the velocity of the ground relative to the velocity of the wheel, there will be no relative velocity, but it's zero, right? So rolling objects that are not skidding, sliding, or something like that are not actually experiencing friction in the way, they're not experiencing kinetic friction, so because they're not sliding past each other. They are experiencing static friction. That is the case. That's actually why they don't slide past each other. So that's an interesting part of this, and then we'll explore more of that later. But two kinds of friction: the kinds of friction where there's no relative motion between the surfaces in contact, the kind where there is relative motion or sliding, a sliding of the surfaces across each other, right? So what causes friction to exist? Well, it's the surfaces themselves. The surfaces are rough. Even if you look at glass up close, if you look at glass under a scanning electron microscope, which is a scanning electron microscope is a device that fires electrons at objects, and electrons map out the surface much more with much more detail than you can with actual visible light. Visible light has very long wavelength compared to the abilities of electrons. So you can't see this with a normal microscope, but if you look at glass under a scanning electron microscope, you see things like this for smooth glass. This is stuff that would be considered smooth, right? You see actual structure, you see real like roughness to it, and it's almost mountainous, it looks like. Glass is certainly not as smooth as it seems when you look at it very closely. It has definite features to it that are rough, and even things that look like they could be canyons or mountains or valleys. There's so many different features on glass that appears smooth and feels smooth to our senses. And it's even true of silicon. Silicon you can make much smoother than glass. But even if you look at silicon, it can be really, when you look at it up close, it can be full of really rough and crazy features. So it's not much different than like a box that's made of wood that definitely has a roughness you can detect with your fingers and your eyes, and concrete, which definitely has a roughness that you can feel and see with your eyes. It's not much different than that. But it's more obvious with a box and concrete. I often like to think of friction kind of like putting your knuckles together. You like make two fists and put your knuckles together, and you can lock them in like that. And then if you try to slide them past each other, you have to get past that lock, right? But once you started moving, it kind of bounces across the top of the bumps, right, of your knuckles. And that's very similar to the static friction. When a box is not moving, those mountains and valleys of the roughness really lock into each other. They find that sweet spot and really get kind of connected. And when you try to push the box, it's locked in, right? And that's the static friction, that locked in kind of action. Once you get it moving and those things start bouncing off of each other, then you're seeing the kinetic friction, which is it's not as much force, right? But all friction is due to this roughness between objects. It's even true. There's one other thing that contributes to this besides just roughness, and that is for objects that are extremely smooth compared to glass, even. You still have roughness, but there's another thing as they get closer and closer together, because they have less of those features that make it feel rough. As they get closer and closer together, the electrons start to interact with each other on the outsides of the atoms of these objects. And that's a little bit different. It's a little bit different kind of thing that can cause multiple things to happen. It can actually cause less friction, and it can actually cause more friction depending on the atoms. So that can play a role, but it usually doesn't play a role in things that we have everyday experience with. If you've ever placed two pieces of glass together, that are very smooth, you'll notice that that they can have this kind of sticky feeling together, right? And that's due to that electrostatic kind of thing. That's also the thing that causes like vinyl stickers to stick to glass and to metal and things like that. That's the same kind of, it's an electrostatic attraction rather than actual friction of any kind. But that electrostatic attraction or repulsion, depending on materials, can actually affect friction. So one of the things that we do to prevent friction between things is to coat them with pencil lead or graphite. Graphite, when it comes very close to other pieces of graphite, other graphite molecules, well, they're actually atoms in a crystalline structure. You could think of them as molecules, I guess, but they're not really molecules. But they're a crystalline structure of carbon. And when you bring graphite together, that electrostatic becomes a repulsion. And so things that have graphite on them don't want to stick together. And you say, well, then how do they make the pencil lead all stick together? That's a good question. What's that? I don't actually know if it is it embedded in some kind of a clay? I don't know that. I didn't know that. So apparently they've got it bound together with a substrate of clay of some kind. But anyway, the pencil lead itself is actually graphite, and graphite does not like to be next to each other. You have a crystal of graphite and another crystal of graphite, they repel each other. And so, you know, if you're locked to your house is sticking, that's because of friction. You take a squirt of graphite, stick it in there, or you rub a pencil all on your key, cover your key with pencil lead, stick the key in there and work it in a few times. It will actually leave some of that pencil lead in there, and the parts within the lock will start repelling each other. They will start not sticking together. So if you're ever in the Cub Scouts and you're going to do a Pinewood Derby, you put pencil lead on your axles and on your wheels so that your car will go faster. I know this. I've won my fair share of Pinewood Derbies. Pencil lead is nice. You can go so much further than that. You can put lead in the front or the back. Oh yeah, there's lots of stuff to do with. I know. My favorite car I ever built, though, my favorite Pinewood Derby car, we made it look like King Tut because my son was obsessed with Egypt at the time. So we made it look like King Tut, and it looked beautiful. It was really well done. And we got my son one of those little multi-tools, and he carved it all out, and then we painted it all and everything. And then we turned it into a car and slid it down the track feet first. But we called it the Carsophagus. Anyway, so friction. Back to friction. Static friction. Static friction is weird because it's variable. Does that make sense to anybody? That static friction is variable? It usually doesn't make sense. But let's try to make sense out of this. A force that is variable, in other words, a force that changes. Why does static friction change? Well, imagine that you're pushing that box, that cardboard box across the floor. We'll use this box as our example. We're pushing this box across the floor and it's not moving. So what do? Let me get my drawing tools out here. The box is not moving. We're going to push it this hard and it's not moving, right? And that's because this static friction is stopping it from moving. This force down here at the bottom is stopping it from moving. So what do? We push harder. Well, does the box always move when we push harder? No, sometimes it still doesn't move. That means that the friction is pushing harder as well. Because if it's not moving, the forces have to add to equal. What is moving?
0.
Yeah, it has to add to 0, right? Because if the box isn't moving at all, it's definitely not accelerating. And force equals mass times acceleration tells us that then the forces have to add to zero if the acceleration is zero. So then we push even harder and it's still not moving. That means that when we pushed harder, the friction started pushing harder too. So it's a variable force. And there is a threshold, there's a point at which you push so hard that the friction can't push back anymore. Why can't it push back anymore? Because you've pushed so hard that you've actually maybe broken one of these mountains off, or you've pushed it so that it's slid up one of these mountains on the microscopic surface, rough surface of the box. You've overcome that locking of the knuckles, essentially. And once you've done that, then the static friction is no longer in effect. The static friction has been overcome. It's no longer variable. You've reached a maximum. So friction, when it's static, has a maximum threshold. And until you get to that threshold, it will just match whatever you push with. If you're not pushing the box at all, is there any static friction? No. The fact that the roughness is still there, it may be locked in like knuckles, but there's nothing preventing any motion because there's nothing trying to make it move. So friction, when it's the static friction, is only present when you try to make it move. And whatever you push with is what the static friction will push back with until you actually get it to move. Right? So it's variable. How do you write that down in science? When something's variable in science, we write it down as an inequality. So this would be properly read as the static friction is, or can be, is a better way to say this in my opinion. When we have an equal sign, that translates directly to the verb to be, is, right? So if it was an equal sign, it would be friction is equal to mu sub s times n, which is the coefficient of static friction times the normal force. But in this case, the less than or equal to sign should be translated, I think, as can be less than or equal to mu sub s times n. Mu sub s is the static coefficient of friction, and that has to do with the two surfaces. It's just what they're made of and how rough they are, essentially. How do you get that number? You look it up. How do they get that number? Well, there's an entire industry of engineers and scientists whose job it is to essentially take two surfaces and slide them past each other and measure how much force it requires to get them moving, and then they write down that number and make the calculation, and they calculate mu for those two surfaces. Literally, there are people that do this for a living. Not a job I would like, but there are plenty of people who get science degrees who want a job that's easy and menial, and it's a 9-to-5 job, and they want to make a decent living and go home and live their life, and that's fine. So they do that. It's a good job for people who can follow a laboratory instruction sheet, I guess. Anyway, the point is that they're doing this constantly, and there are repositories, huge, endless repositories of static coefficients of friction out there, if you want to know what they are. They're generally only good if you have the exact materials that they've tested. So so if you come across a new pair of materials, you're going to have to do it for yourself. It's not hard to do. In fact, we'll see how it's done here later in this section. But this table here has a few of these coefficients of friction. Rubber on dry concrete is a static coefficient of friction of 1. And I think that's the rubber we use today for our wheels in our cars. Our wheels in our cars today use synthetic rubber made from petroleum products. And synthetic rubber that has been vulcanized actually has a really good coefficient of friction. It's much better than natural rubber. Natural rubber actually comes from a tree. It's the sap from a tree in South America, and they also grow them in Africa. I don't know if it's native to Africa or not, probably is. They probably have their own native version of it, but it's also in Southeast Asia, they grow these trees. And that's generally the kind of rubber that's kind of clearish, beigeish in color. You sometimes see it on the bottom of shoes. I don't have shoes with natural rubber on them, but I do have a pair at home that have natural rubber on them. But if you look at old car tires back in the early 20th century, in the late 1800s, the late 19th century, and old bicycle tires from that era, they were made of this tire, this rubber that was natural rubber, and it kind of had after it'd been on dirt roads for a while, it kind of had a brown look to it, but it certainly wasn't the black color we have today. That stuff, the natural rubber, does not stick as well to concrete, and so it actually has a lower coefficient of friction. Higher coefficients, they stick more. Lower coefficients, they stick less. You can see it on wet concrete, it sticks less, significantly less, right? And that's what we would expect, because when you're on wet concrete, you hit the brakes, your car tends to slide further if you lock up your brakes, right? Your car just tends to slide at all on wet concrete. Sometimes it won't even slide on dry concrete. Wood on wood, it's 0.5. Wood slides against wood, especially if it's hardwoods. Hardwoods like oak, maple, they slide past each other extremely well. Waxed wood on wet snow. That's skis, essentially, right? Skiing is that, 0.14. Dry steel, 0.6. Oiled steel, 0.05. Right? That's why we put oil in our car engines. Teflon on steel, 0.04. Bone lubricated by synovial fluid, 0.016. That's the lowest one we've got here. And most of the lowest coefficients of friction we have in the universe are natural things that exist naturally. We've not been able to really reproduce these low coefficients of friction with materials very well. We're going to be able to do it with magnetic fields, but not with materials very well. And notice here that we have a static coefficient of friction and a kinetic coefficient of friction. So this is the static coefficient of friction is when they're not moving, of course, but it changes when it's kinetic, and you can see that it goes down, which is what we thought it should, right? We're trying to move the box, we're pushing harder, and eventually we get it to move, and once we get it moving, it's easier to keep it moving than it was to start. And that's because the kinetic coefficient of friction is lower in all of these cases. Right?
Teflon on steel has the same coefficient of friction for both moving and static.
It does, but that's not actually true. The Teflon on steel coefficient of friction is slightly less when it's moving, but it's not much.
Oh, just a very small difference.
Very small difference. And it's the same you see with bone and synovial fluid. It's just slightly less, right? And so it wouldn't surprise you to know that when they replace a hip joint, they replace it with Teflon coated with a Teflon coated bone in a socket made of steel, or vice versa. I can't remember which way it goes, but it gives you a very low coefficient of friction, but it also doesn't change much that when you're moving versus when it's stopped. And that's good, because when you get up in the morning, and well, you may not know, none of you might be old, you might not be old enough to really experience this a lot, but if you've ever worked really hard one day and then the next day, and maybe didn't drink a lot of water, and the next day you get up and you're kind of stiff, like you get up and what's that?
This is every day.
That happens every day to you? I didn't experience it much when I was a kid, when I was in my teens and 20s, but I started to experience it. I started to experience it when I got older in my 20s. But I certainly experience it every day now. Every day I get up and I have to move my body to get the synovial fluid flowing, because the synovial fluid is essentially a fluid of proteins. And proteins, if you want to know what proteins feel like, blow your nose, or look like, blow your nose. When you blow your nose, you're essentially blowing proteins out of your body. It's gooey, slimy, slippery, nasty stuff. That's what it is. And synovial fluid is essentially protein fluid. And it has a very low coefficient of friction when you put it on a surface of the bone. The other thing that's in your sockets is cartilage. which is also made of, you got it, proteins, right? And proteins tend to be very slippery, right? And so you have these very slippery things against these very slippery things, but you lose synovial fluid when you don't drink liquids, and you don't produce as many synovial fluids as you get older. It's just your body just starts not doing these things as well. And so you really don't want to have no synovial fluids. Like I had a friend that had a joint in his ankle, all of his ankle and foot actually. He couldn't produce synovial fluids down there for some reason. And eventually all the friction and grinding actually wasn't even eventually, it happened when he was very young. The grinding and the friction down in his foot caused his bones to fuse together. So it created a bunch of calcium buildup as the bones ground down, all that stuff made it, and he couldn't move his foot at all. And when I knew him in college, he always had to go around he carried around kind of a modified crutch essentially, because his one foot was completely immobile, couldn't walk on it, couldn't use it at all. And the really crazy thing is that he'd kick my butt in basketball with one foot. One foot, and he'd be using his crutch. He was a really good athlete. He was phenomenal at basketball, and I could not beat him. I didn't even I wasn't even trying to be nice and not play hard. He would just kill me. Anyway, so lots of different coefficients of friction for static and kinetic friction. How do you use this equation for static friction? Well, you use it, sorry, this one up here, this inequality for kinetic friction. You essentially use it as you would use an equation. You don't really use the inequality mathematically. You just replace the inequality with an equation, and you calculate the maximum amount of force that you can put on. That will tell you the maximum amount of force you can push on an object without making it move. But if you're pushing on something and you're not making it move, so that means that you have less than an amount of force, and you can calculate the friction by just saying, how hard are you pushing, right? So if I come up to you and say, oh, you're trying to push that box across the floor, how much and it's not moving. And you say, yeah, how much friction is preventing me from pushing this box? So I said, well, how hard are you pushing it? I'm pushing with 10 Newtons. Well, that's how much friction is pushing too, because it's pushing back with whatever you're pushing with. And this is something that confuses a lot of people when they're doing their homework. The problem might say, it might say you're pushing a box across the floor, just like we're talking about, and you're pushing with 25 Newtons of force and it's not moving. How much static friction is there? And people will immediately go to this equation and try to calculate it. But you don't have to calculate it. They've told you, because the amount that you're pushing with has to equal the amount of friction, because it's not moving, right? You're pushing with 20 Newtons, it's not moving. That means the friction is pushing with 20 Newtons because the forces have to add to zero. And that means that the maximum amount of frictional force is more than 20 Newtons. You have to push harder to find out what that is, or you have to know the static coefficient of friction and calculate it. The other thing that you have to know is you have to know the normal force. And when the box is on a horizontal surface, the weight is pulling the box down, and the normal force is preventing the box from falling through the floor. And those two things are equal and opposite when you're on a horizontal surface, right? However, there are a couple of things that can affect the normal force. If instead of pushing horizontally, you push down on the box, you have a component of your push that's pushing the box down more, which means the normal force is going to be more. Because the normal force has to equal all of the downward forces on the box. It has to be equal and opposite to that on a horizontal surface. So if you're pushing slightly downward on the box, then you're going to increase the normal force upward on the box. If you're pushing slightly upward on the box, then you're going to decrease the normal force on the box. And we all know this, practically speaking. If you're trying to get a really heavy box moving, it helps to lift it up a little bit to reduce the contact with the ground a little bit. It helps a little bit to do that. So you get on the other side of the box, and instead of trying to push, you pull on the box and you pull it upward, because naturally that works better. And that helps you to slide the box a little bit better. Pulling upward helps because it reduces the normal force from the floor to the box. The other thing that you have to be aware of when it comes to the normal force is that the normal force is not always equal to the weight, because sometimes you're on a slope and the weight of the box is this way, but the normal force on the box is this way, right? And then you rotate your axes to a parallel and a perpendicular axis system, right? And you resolve the components of your weight into a perpendicular weight and a parallel weight component. Those two components add together to equal the total weight of the box, W, and only the perpendicular weight is going to be equal to and opposite the normal force, right? So it's only part of the weight is equal to the normal force in that case. And we'll see plenty of examples of that in this section. So here's your kinetic friction equation. It's actually the same format as the static friction, except it's got an equal sign, right? And of course, the kinetic coefficient of friction is different than the static coefficient of friction. If you graph out the amount of force to move a box that's sitting on the floor, you'll increase your force, increase your pushing force, increase your pushing force in the static region. This is all static friction that's pushing back. And as you increase your push, the static friction is increasing, but eventually you get to the point where the box starts to move. Once the box starts to move, the friction goes to a constant value, a constant-ish value, right? And that constant-ish value is going to be the same value as long as you're pushing the box. Doesn't matter how hard you're pushing it, doesn't matter how fast it's moving. The friction will be constant after you get it moving, a constant-ish. It's not always perfectly constant because the surfaces aren't always perfectly uniform. So let's take a look at an example. Here we have an example. You're trying to push a crate. The crate has a mass of 100 kilograms, right? And so we calculate the weight of the crate to be 980 newtons, right? And we're trying to push the crate, but the static coefficient of friction with the crate, let's see, they're not actually doing that, are they? Yeah, they are doing that. Yeah, so we're going to calculate the maximum static coefficient of the crate with the floor to be 0.45 times 980 newtons, the weight of the crate, because it's on a horizontal floor, so the weight is equal to normal force. So what this tells us the amount of force we have to push with if we're going to get it moving from a standstill. We have to push with at least 440 newtons to get it going. But afterwards, after we get it going, we only need to maintain 290 newtons because the kinetic coefficient friction is 0.3 as opposed to 0.45. So what would you say if I came along and said, you're trying to push this crate and you're going to push with 200 newtons of force? What's friction?
200 newtons.
200
Right.
newtons, right? Why?
Because assuming if the box is not moving, it's because it's just pushing back at the same amount.
Why is the box not moving? Because I didn't actually say that. I just said we're going to push with 200 newtons of force. I didn't say it wasn't moving. How do you know it's not moving? Because it's less than 440 newtons, right? 440 newtons tells you the threshold. So if you push with less than that, it's not moving. So you can immediately just say, oh, the friction is equal to 200 newtons as well. That's on a horizontal surface. If it's at an angle, you're going to have to measure the normal, you're going to have to calculate the normal force. And that happens a lot. So if you're at an angle, you calculate the perpendicular component of the weight, and that will be equal to the normal force, and that will be your new threshold, right? Because it happens all the time where you put something on a surface that's at an angle, and it just stays there, right? It doesn't move, it doesn't slide. Why? Well, because the perpendicular component of the force, of the weight force, creates a normal force that is strong enough to make a static coefficient of, or a static friction force that is stronger than the parallel weight force. Yes, sir.
Are we going to, in this class, have to worry about these problems that have to do with me applying a force on an object tipping to the moon because of friction?
Yes, but not till chapter 10. Yes. As you might imagine, causing things to rotate is a little more complicated than just pushing objects in lines. So, but we will do that by the end of this class. Yeah. Good question. Okay, so we're done for today. That hopefully will get you started on some friction problems. We will come back to the friction idea and do some examples on Friday. And also we will talk about drag on Friday. No, yes, drag and centripetal force on Friday, which are actually two of the simpler topics. So we should be able to get through those pretty quickly. So have a good day. And I will answer any of those questions that were sent to me by MyOpenMath as soon as I can as well.
You have a good day.
See you later. Thank you. You too.
Thank you, Mr. Daly.
Thank you.